Hello. So we have discussed the problem of simple pendulum in detail using the Lagrangian approach. Now let's finalize a recipe for solving problems using the Lagrangian formulation, and it will always help you to just follow some standard procedures, standard steps, which will actually give you the conceptual solution to a given problem. So in any mechanical problem, when you're going to use the Lagrange's equation of motion, these are the five through. So as you have seen, you can begin by identifying the degree of freedom of the given system, and you have got some standard methodology to find out the degree of freedom of the given system. The first and foremost thing is to see how many particles are there or how many masses are there. So that is what we just label as capital N. So depending on the number of particles, you can first think of how many degrees of freedom without considering the constraints present. So you know that if you neglect the constraints, then the number of degrees of freedom for a body which is free to move in space, three-dimensional space, it should be 3n. 3n degrees of freedom is usually there. So for one particle, there will be 3 degrees of freedom, and thereafter you think of how many holonomic constraints are there. Only the holonomic constraints will reduce the degrees of freedom. So if there are holonomic constraints expressed in k equations, then the number of degrees of freedom will be reduced to 3n minus k, and that is the thing that will be using, where n is the number of particles of the system. So you obtain the number of degrees of the freedom after deducting the holonomic constraints. Then once you identify the degree of freedom of the given system, the next task is to identify a suitable set, a convenient set of generalized coordinates. That actually with the experience of solving the problem, you will be getting an idea how to choose the proper generalized coordinates. Okay, a bit of logic and bit of intuition will be helping you to easily identify the suitable set of generalized coordinates. One thing you can remember always, the number of generalized coordinates required, that is qj's, right? This is not generalized coordinates, qj's. The number of generalized coordinates required will be equal to the j runs from 1 to n, where n is the degree of freedom. So if a system has got 3 degrees of freedom, then we need to have what? 3 generalized coordinates. If a system has got only 1 degree of freedom, then we need to have only 1 proper generalized coordinate. Okay, that's the idea. Then once this is done, the rest is purely mechanical or mathematical. Obtain the potential energy V and the kinetic energy T of the system as function of generalized coordinates, means V as a function of generalized coordinates qj, and see the T as a function of the corresponding generalized or conjugate generalized velocity qj dot. So this is what you have to do, and thereafter form the Lagrangian of the system, which is a critical step, okay, as T minus V, where T is a function of qj dot, okay, and V is a function of what? Qj, right? Then final step, substitute this Lagrangian, okay, which is expressed as function of qj and qj dot, generalized coordinate and generalized velocity, in the Lagrange's equation of motion for the particular system, and then just solve it. Okay, analytically you can just find the solution to that differential equation, right? So then this is the thing, find a d by dt of dou L by dou qj dot. For every degree of freedom, you have to write an equation and then solve it, minus dou L by dou qj is equal to 0. Solve it, you will get the required result, right? So once we finalize this recipe, let's go and solve one more such problem. And I suggest you that take variety of problems, both familiar and not so familiar. You can get the problems from all those standard textbooks or some reference books that I have already uploaded in your Google Classroom. You can refer to it. Take enough number of problems until you feel yourself confident of solving any mechanical problem of that sort. Okay, so I don't tell you that to solve only 10 problem, 15 problem. No, it's not the number of problems that you solve, rather it's how much you become confident after solving the problem. So maybe you solve only 5 problems, but if you are confident that I can solve any number of problems in the same manner, if you are thorough with the recipe, if you are thorough with the concept, okay, then it's enough. But your confidence should be reflected whenever you attempt a competitive examination, right? So I leave the number of problems to you, how much to decide. But see that you always do some standard problems at least, okay, so that you will get always an edge in analytical mechanics. Okay, so I think I can go to the next example for the application of the Lagrange's formulation. Okay, so that's quite a familiar example I am taking, which is nothing but our Atwood's machine. Hope you remember in one of the lectures, one of the introductory lectures, in order to show you how the Newtonian mechanics works, we have discussed the Atwood's machine, right? The pulley mass system, which is one of the standard problems, the toy problems in mechanics. Now, there, hope you remember the results also, maybe it's with you. There, what you did was you identify the forces. You identified the forces acting on each of the masses. It was the weight m1g, m2g, and the tension that is along the string, and thereafter you wrote the force equations using free body diagrams, and then you solved for it. Okay, now we are going to solve the same problem, the Atwood's machine problem, by the Lagrangian method. And you know, in Lagrangian method we are using the concept of generalized coordinates, which will take away or which will bypass the problems, difficulties caused by constrained forces. So it was a method to bypass the constrained forces involved in the problem. Okay, so let's see how to do this one. Okay, so now let me try to follow the recipe. Okay, until you become until the recipe is fixed in your brain, I'll be trying to just refer to the recipe step by step, right? So that you will be finally feeling maybe comfortable with whatever type of problem that we are dealing. Okay, so see, what was the first step that we had to do in the recipe? You know, it was to identify the number of degrees of freedom of the given system. So let's see how to do that. See, how many particles are there in the Atwood's machine problem? You know, there is m1 and m2, so there are 2 particles. So I say there are 2 particles, so I'm writing here that yes, n equal to 2. So this is our background work. With the practice you can just do this within a fraction of seconds. Okay, so n equal to 2. Now if these m1 and m2, I'm giving you some thought process which will help you. You can directly, with the experience, you can write that how many degrees of freedom and all. Logically you can directly come to the conclusion, but let's do that straightforward also. Okay, so n equal to, so if m1 and m2 were free to move in space, 3-dimensional space, how many degrees of freedom should it have? ഈ രണ്ട് മാസും സ്പേസിൽ മൂവ് ചെയ്യാൻ ഫ്രീ ആയിരുന്നുവെങ്കിൽ എത്ര ഡിഗ്രീസ് ഓഫ് ഫ്രീഡം ഇവരുടെ രണ്ടുപേരും ഈ കോൺഫിഗറേഷനെ ഡിസ്ക്രൈബ് ചെയ്യാൻ എത്ര ഡിഗ്രീസ് ഓഫ് ഫ്രീഡം ആവശ്യമായിരുന്നേനെ? തീർച്ചയായിട്ടും 3n ഡിഗ്രീസ് ഓഫ് ഫ്രീഡം ഉണ്ടായിരുന്നേനെ അല്ലേ? ഇസ് നോട്ട് m1ന് x1 y1 z1 കോർഡിനേറ്റ് ആവശ്യമായി വന്നിരുന്നേനെ, m2നും x2 y2 z2 ആവശ്യമായി വന്നിരുന്നേനെ. ഇഫ് ദേ വർ 2 ഫ്രീ പാർട്ടിക്കിൾസ് ഇൻ സ്പേസ്. ഓക്കെ, അപ്പോൾ നമ്മൾ പ്രതീക്ഷിക്കുകയാണ് 3n. ഓക്കെ, 3n എന്ന് പറയുന്നത് എത്രയാണ്? 6 ആവശ്യമായിരുന്നു. പക്ഷേ ഇതിൽ നമ്മൾ ഇനി കൺസ്ട്രെയിൻറ്റുകളെ പറ്റി ചിന്തിക്കണം. സിസ്റ്റത്തിൽ ഹോളോണോമിക് കൺസ്ട്രെയിൻറ്റുകൾ ചിന്തിക്കണം. എന്തൊക്കെയാണ് ഹോളോണോമിക് കൺസ്ട്രെയിൻറ്റ്സ് നോക്കി ഇവിടെ? ഒരു ഹോളോണോമിക് കൺസ്ട്രെയിൻറ്റ് വളരെ ക്ലിയർ ആണ്. നമുക്ക് എടുക്കാം, ദേ ആർ കണക്റ്റഡ് ബൈ ദാറ്റ് ഇൻഎക്സ്റ്റൻസിബിൾ സ്ട്രിങ്, ഒരു റോപ്പ് അല്ലേ? ഓക്കെ, റോപ്പ് ഓഫ് ലെങ്ത് L എന്ന് നമുക്ക് എടുക്കാം. So the total length of the rope L. So you know that L is a constant. L is fixed on unstretchable string on which passes over the frictionless pulley. Okay, we are neglecting the mass of the pulley, and even the size of the pulley can be taken as negligible. Okay, so L equal to a constant. അപ്പോൾ ഒരു കൺസ്ട്രെയിൻറ്റ് വന്നു അല്ലേ, അതായത് m1 മാസ് എത്രത്തോളം താഴേക്ക് നീങ്ങുന്നു. Okay, if m1 is greater than m2, let me assume like that. Okay, let m1 be greater than m2. I'm just making an assumption like that. അപ്പോൾ m1 എത്രത്തോളം താഴേക്ക് നീങ്ങുന്നു അത്രത്തോളം m2 മുകളിലേക്ക് നീങ്ങും. Right? So you can see that it's due to the constraint that is L equal to a constant. Okay, so L equal to a constant. That is one of the constraints. Ini where are the constraints undo? So let's assume that this okay, pulley is moving, or the masses are moving along y-axis. Right? Masses are moving along y-axis. So that is the idea. Now we can see that if the masses are moving along y-axis, it's only one axis. Right? Okay. So I can say the coordinates of m1, z1 is equal to a z1 equal to, you fix 0, z1 equal to 0, z2, what is z2? The z coordinate of m2, that is also equal to 0. Similarly, I can say x1, the position of okay, is not this, what do you say, m1 is fixed, so I can say that x1 equal to constant is say c1, and x2 is also equal to a, and some other constant maybe, okay, along x direction you can take any of the c2. So can you see that I have got how many equations which represent constraints? L equal to a constant, so I have got altogether 5 constraint equations. So I can say here k equal to number of holonomic constraints is equal to 5. So what will be the number of degrees of freedom after all these things? So it will be 3n minus k. So this is a standard procedure. Only to make you familiar with the procedure, I am just giving you this one. Okay, so it will be 6 minus 5, which is equal to 1. So what does it mean? The number of degree of freedom of this particular system is what? Only 1. Why 1? Because the reason is well and clear. Why? You need to specify only one coordinate, either of m1 or of m2 at any instant. Okay, for example, so let me do one thing. Let me, we have to anyway calculate the potential energy of the system. So for that, let me fix the reference level. So what I'm going to do is that I'm going to fix the reference level here. So let me say that this is V equal to 0. This is the 0 of the potential energy. Okay, V equal to 0. So, and let me say that this particular, see from here, let me measure. Let me say that this is Y. Okay, I'm taking this is Y axis. You can take it anyway. And so okay, if you neglect the size of the pulley handle to make it easy, if the pulley has got a radius r which is not negligible, then you have to take some 2 pi r or pi r, etc. That's yet another method, more accurate method. I'm just going for a rough method, neglecting the size of the pulley. So if L is the length of the string, I can say that this one should be L minus y. What will be L minus y? This is L minus y, because the total length is equal to L, right, of the string. So this is the thing. Now with these considerations, let me write down the potential energy and kinetic energy. Okay, so first step is already over. I have introduced the number of degrees of freedom, so I'm writing it here, degree of freedom n equal to 1, since L is a constant. That is the reason. Okay, just you need to know y, the y coordinate of one of the mass, then automatically the y coordinate of the second mass is fixed. Okay, if y1 equal to y, then y2 equal to L minus y, means only y is needed. Y is the only independent coordinate. Okay, n equal to 1. Therefore, if n equal to 1, you know the degree of freedom is equal to 1. How many generalized coordinates are needed? Only one generalized coordinate is needed. Okay, so why don't you take the generalized coordinate as y itself? That is enough, because that is the simplest single Cartesian coordinate. So therefore q is equal to y. So the first step or the second step also is over. Now what is the third step? Third step was to just find the kinetic energy and the potential energy separately as functions of generalized coordinate, or generalized velocity and generalized coordinate. So if q equal to y, then you know q dot is nothing but y dot. You know y dot is nothing but dy by dt, the velocity. You could have taken as x, then it would have been dx by dt, whatever it is, x or y doesn't matter for us. So that is that. So now I'm writing the potential energy. Okay, so this is the third step actually, the total potential energy. Total potential energy, okay, of the system. That's why I'm just taking the okay, what do you call total potential energy of the system, okay. So for that only I have fixed the reference level. V equal to 0 is at the top point. So what will be V equal to? V will be equal to, see, V is equal to usually mgh, okay, mgh. Now the reference level for height is here. So what will be the potential energy of m1? m1 I am writing minus m1 g into, instead of h it will be y. It's not from here to here, that is y. Okay, so up to here you say whatever it is, up to the center of mass or something like that. So minus m1 gy, that is the potential energy of the first mass. Similarly, minus, okay, m2 g into h. What is the height from the height or the position from v equal to 0? That is L minus y. So it will be minus m2 g into L minus y. Hope you understood why I have taken minus. The reason is well and clear. That is due to the fixation of the reference level. We have already seen that one in the previous video. I have fixed the 0 of the reference level above the masses. So the potential energy of the masses below the reference level will be taken as negative. Okay, and if you are and it's always good that you fix the 0 of the reference level at some fixed point. Okay, you can even think of that. Can't you fix the 0? Can you fix the 0 of the reference level at m1? Better not. Why? Because during the motion of the system, during the dynamics of the system, the reference level will be getting shifted. That is not fine. Okay, that will make our calculations much more complicated. So always fix the 0 of the reference level at some point of the problem which is fixed. Okay, with reference to which you can just make all the potential energy calculations. Okay, so better I can fix it to the pivot point or to the convenient reference fixed point. So this is what. So V. So let me just modify this one. Okay, so therefore V is equal to, I'm just rewriting this one. There are two terms with G, right? There are two terms with Gy, right? First term and last term will be Gy. So let me combine it here. So it will be equal to, minus will become plus. So it will become, I'm just writing it as here, m2gy. So I can take m2, okay, m2gy is there, minus m1gy is there. So I am taking gy as common. So it will be m2 minus m1 into gy, just for the sake of simplification. So what will be remaining? The third term will be the minus m2 GL. This term is there, minus m2GL. Let me say that this is my first equation to begin with. That's the potential energy, right? So can't you see that the potential energy is expressed as a function of the generalized coordinate y alone? So this is V of y, VQJ, V of y. You can see the y comes over here, and whatever other terms are remaining is only constants. M1, M2, GL, all are constants. So it's a V is a V of y. Right. Now, same manner you can write the kinetic energy, total kinetic energy of the system, total KE of the system. Okay, so that's the thing. Now we are writing T is not for kinetic energy. T is equal to, how many terms of kinetic energy will be there? There will be two terms because there are two masses. Kinetic energy is equal to half mv square. So it should be equal to half m1 v1 square. Okay, v1 is the velocity of the first mass, m1. So I can write v1 as y dot, is it not? So my dot, okay, half mv square. Here the generalized velocity is the linear velocity along y direction. So plus half m2 into, okay, see what is the coordinate of just m2? it is L minus Y. So if you want, I can write it like this. I can directly do that one. D by dt of L minus Y. That will be the thing. Whole square. I need not complicate it like this, but let me write it like this. So so that you can understand what's the mathematics. So it is half m1 y dot square plus half m2. What's the result finally? That you do d by dt of L minus Y. You know L is a constant, so d by dt of L is 0. So d by dt of minus y is minus y dot. So minus y dot square. That is what? Simply y dot square. Is not y dot square itself. Okay, dl by dt equal to 0. That was our assumption, right? Why? The length of the pendulum is a constant. So it's quite simple. You can directly even write that one, because if you know, it depends only on the speed, not on the direction. So it will be y dot will be the case. You know, if m1 is coming down with y dot velocity, v velocity, sorry, the v speed, let me say speed. If m1 is coming down with v speed, then m2 will be going up with the same v speed. Okay, that is why you can see the kinetic energy will be the speed term in both the things are about the same. So which I can just simply write as okay, can't you write it as half times m1 plus m2 y dot square. So that's my second equation. And can you see that this t as required now has turned out to be a function of y dot. So t a function of qj dot. So it's t a function of y dot. So we have completed the second step of the recipe. Now finally finding the Lagrangian, right? So now the Lagrangian of the system. Lagrangian of the system. See that you write whatever just words. Lagrangian of the system. Okay, just writing L is enough, but let me write it full. Okay, so that it becomes fleshy, right? Otherwise the problem will be bony. Make it fleshy. Okay, that seems good. T minus v. So it's equal to simply half, just a matter of substitution, half times m1 plus m2 y dot square, right, minus that first equation. What is that? m2 minus m1 gy, right? Then that minus will become plus m2gl, plus m2gl. That's my third equation, and this is a quite relevant step. Okay, so this is a very important step. Obtaining the Lagrangian is a crucial step in the solution of the problem. This is the Lagrangian of the Atwood's machine, right? One of the Lagrangians. Okay, you may think of some other Lagrangian if possible. Okay, as I told you, the Lagrangian need not be unique. Okay, it can be unique, need not be unique. All these. See, so that is it. Now once you got the Lagrangian, you know what is left with. Just substituting in the Lagrange's equation of motion. So let us write the Lagrange's equation of motion so that we get a motivation. Okay, Lagrange's equation of motion for this particular system. How do you write it? It was d by dt of time derivative of total derivative of dou L by dou qj dot. What is dou qj dot? Q dot is y dot. So dou L by dou y dot. In our problem it is y dot minus dou L by dou y, dou qj, dou y. Okay, dou L by dou y, take it as y is equal to 0. That is our target equation. So now it will give you, writing this equation will give you what are things I have to find out. I have to find out dou L by dou y dot and dou L by dou y. Let's do it in the next step. Okay, so I think I can just take this Lagrangian equation along with me. Okay, so just a moment. Yeah, just a moment. Yeah, so I have the Lagrangian here. This is the Lagrangian. Now what do you have to find out? I have to find out the see dou L by dou y dot, right? Dou L by dou y dot. So let me find out dou L by dou y dot. Dou L by dou y dot. It's quite easy, you know, because it's not complicated. So only which term is having y dot? The first term here is having y dot. So taking derivative m1 m2 are constant, it will be 2y dot. So 2 and 2 will be getting cancelled. So it will be equal to simply m1 plus m2 into y dot. Won't it be? That would be the thing. m1 plus m2 into y dot. So that is your dou L by dou y dot. Let me call see what was our previous equation. Let me have a look. Yeah, equation number 3. Okay, so let me say that equation 4 was over. So this is equation number 3 itself, and let me say that this is some equation number 5a. Okay, similarly, and dou L by dou y also we need. Okay, what is dou L by dou y? You know that only terms involving y will be affected, other terms will vanish. So second term, so what is that? That will be equal to minus, that y will be gone, that's all, minus m2 minus m1. Be careful about the signs, please. That's okay, sometimes relevant. Okay, so minus into g, that y is gone. The first term and third term will vanish, of course. So let me say that this is my 5b equation. Now can't you substitute these two things in back to the Lagrangian equation, equation number 4? Yeah. So what is equation number 4 becoming? So therefore equation number 4 will become d by dt of, d by dt of dou L by dou y dot. What is dou L by dou y dot? That is m1 plus m2 into y dot. Okay, into y dot. Then minus, there it was a minus, then dou L by dou y. What is dou L by dou y? Dou L by dou y is 5b. That is minus m2 minus m1 into g. That should be equal to finally 0. This is the thing. Now it's quite easy. m1 and m2 are constants. So it will be d by dt of y dot. D by dt of y dot is what? Y double dot. Okay. So this is m1 plus m2 taken as constants outside. Then into y double dot. Minus and minus will become what? Plus, right? Minus minus, it has become what? Plus. So it is plus m2 minus m1 g is equal to 0. Plus m2 minus m1 g equal to 0. So now what's your aim? Yeah, what is our aim of doing this adverse machine problem? To find out the common acceleration of the masses. Common acceleration. I'm calling it as common acceleration because both the masses will be moving with the same magnitude of acceleration. One will be accelerating downwards, the other will be accelerating upwards. That's all. With the common acceleration a. And what will be a? We have taken the coordinates to be y. Okay. So y dot is the velocity. Velocity is equal to y dot. So acceleration is equal to nothing but what? dv by dt, which is what? Y double dot. So acceleration is nothing but y double dot. You could have taken the vertical direction as x, then it would have sounded x double dot. It doesn't matter whatever symbol you use. So acceleration, therefore acceleration of the mass system, acceleration y double dot. What is that? You can just modify, take one term to the other side. So it will become m2 minus m1 will become inverted, that is m1 minus m2, okay, into g divided by the coefficient of y double dot, that is m1 plus m2 divided by m1 plus m2. And I hope that you do remember the result. This result you might be remembering because we have seen that it was the same acceleration that we have derived by following the Newtonian method. Okay, so you can see that the same result we are able to get, which was produced by the Newtonian method. Okay, so y double dot is nothing but acceleration a of the masses, common masses. And I think you might have noticed that during the solution of the problem, nowhere we have considered the vector nature of the quantities. What only we did was we calculate the kinetic energy, which is a scalar, we calculate the potential of the system, which is yet another scalar, and then from those two scalar quantities, taking the difference, you obtained the Lagrangian of the function or Lagrangian of the system, which we had defined as a proper well-behaved function, which contains all information that is related to the given system. That is why the Lagrangian of the system assumes what? Importance. So you can see that the information like acceleration of the system was obtained from the knowledge of Lagrangian of the system. Okay, so we can say that this method has got an advantage. What is the advantage? You need not be aware of the tension force. Is it not? You never calculate the tension force T in the strings. So tension is not found out, right? So this is at the same time a strength and weakness of the Lagrangian method. The advantage is that it is not necessary to know the equation of constraint. Okay, means the tension force to solve the problem. But the disadvantage is that there is no way to find out the tension, because that is a vector quantity that is involved. For that, we have to go to what you call as what the Newtonian method. Okay, hope that this problem has given you more idea regarding the technique of Lagrangian formulation. We will work out some more problems in the coming sessions. You can also go on referring to the textbooks that I have already uploaded. Thank you.